So I'm going to begin today by introducing our three speakers. The first one is Babak Ashuri, who is an assistant professor in the School of Building Construction. His current research focuses on the identification and evaluation of flexible technologies and systems for sustainable buildings and the development of real option models for financial assessment of highway projects under traffic uncertainty. Dr. Ashuri holds a PhD in Industrial Systems Engineering from Georgia Tech. Our second speaker is Javier Irizarry, and he is an assistant professor in the School of Building Construction. His research focuses on developing next-generation technology-enhanced solutions to construction environment problems by incorporating the cognitive processes of the human component of construction operations. Dr. Irizarry holds a PhD in Construction Engineering and Management from Purdue University. And our last speaker today is Gernot Rieger, and he is an assistant professor in the School of Architecture. His research focuses on using digital technologies to improve architecture's relationship to a natural, built, and social environment. He holds a Master of Science in Advanced Architectural Design from Columbia University and an engineering diploma in architecture from the University of Innsbruck. Please join me today in welcoming our three speakers. And we will begin with Dr. Ashuri.
All right. Good morning, everybody. Thanks, Leslie, for the introduction. Thanks for everybody being here. Thanks for the library staff. As Leslie said, I'm Babak Ashuri. I'm assistant professor over in the School of Building Construction. I'm directing a research lab there, Economics of the Sustainable Built Environment. The topic of my talk today, as you can see, pricing flexibility in solar-ready homes. What I'm going to talk in the next few minutes is a new evaluation method, a new valuation model for investment in sustainability, particularly investment in kind of flexible design that can be incorporated for sustainability, and in this case in particular, renewable energy for buildings. Here is an overview, and let me get to the bottom of it. Everybody, you talk in the construction industry, in architecture, engineering, construction, talk about sustainability and huge amount of investment from the public sector and private sector into sustainability, renewable energy, and things of that kind that help us save energy, produce energy on site, and it's large, it's huge. As far as now, put some dollar values, you can see it's huge and it's rising. It's already up there. And the major problem from the practical side is this valuation is not addressed correctly. Most of our valuation techniques are based on return on investment, payback period, or net present value, which really doesn't capture some of the fundamental features of these investments. And I'm getting to that. And one of the most important limitation here is most of them assume that you have a fixed business strategy, fixed investment, and you have to value that fixed investment. In other words, that you have a fixed design, fixed strategy for design and construction, which cannot be changed, or you cannot incorporate it in multiple phases. And the reality is not like that. Reality is usually this investment happen over time in the multi-stage, and we can capture several sort of investment strategy that are flexible, can incorporate some flexible design technologies to enhance the value of investment, to minimize exposure to financial risk. And what I'm proposing here is a new valuation method to overcome the limitation of current valuation techniques. So the gap is that investment timing. Currently, that investment timing is not part of the equation. So it's not just investing today or never. It's just about when would be optimal time to invest, and what would be the investor risk profile under all sorts of uncertainty, considering that optimal time for investment. So basically, I'm proposing, instead of using conventional methods like net present value, kind of basic engineering economy that some of you might be familiar, I'm proposing using option theory, because these are really options for investment. I mean, you can exercise it as an owner, as a property manager. You can exercise it at any point in the life cycle of a building. It's not just immediate investment. And you're looking for enhancing the monetary value and minimizing the risk profile of that investor over the life cycle of the building. Let me talk a little bit about the flexibility, and here is something that I would like to hear back from you in the Q&A section. I would like to see a good example, good flexible design strategy, not just for the sustainability. It could be flexible workspace, it could be flexible AC system. The thing is, what can this flexibility bring to the table? And the example I have here is solar ready. I mean, solar technologies, photovoltaic, panels. The past decade, the price dramatically dropped. But many homes, many buildings cannot use that because it requires some additional costs. It's not just purchasing those panels. It requires, wiring. If you want to use it for heat water, you need to do some piping, and you need to have a structural support for that, additional structural support to put like PV panel up in roof. So the problem is many of these buildings or many of these homes did not consider that possibility 10 years ago, 20 years ago. The technology was kind of emerging, and there might be other technologies emerging. Are we prepared? And what I'm arguing, with very little investment up front and with consideration in design and construction phase, we can get the benefits in the future by incorporating those flexible strategy up front. So that's kind of challenging the conventional wisdom in terms of fixed design. So we like to have flexible design in order to help us achieve sustainability in future at the lower cost and higher expected value for the in terms of monetary value and benefits for the owner. There are a lot of barriers for this energy efficiency, renewable energy. I listed that, 20 factors here. What I'm mainly focused here is kind of cost effectiveness and fiscal barrier. What I'm saying, at the end of the day, for whatever value system you have, it should make economic sense, and how we can make a business case for sustainability. And what I'm arguing, flexible technologies like that, solar ready, can help owner to achieve higher level of investment value. Again, this is an overview of conventional metrics like ROI, payback period, and the limitation is they don't consider that timing. And that timing sometimes, ends up to overinvestment, sometimes underinvestment. So that timing is really key. If we want to achieve certain environmental goals in terms of energy reduction, we need to not waste capital. That capital is limited. A smart investment help us achieve better utilization of the existing capital, limited capital. Real option can consider investment under uncertainty and also consider timing as part of that. That's what I'm going to use and apply for this problem in hand. Here is an overview of the research method. We basically, for any economic analysis, we need to have some sort of life cycle cost and benefit analysis. So we need to have some idea about what would happen on my energy saving side, in this case, renewable energy production coming from the photovoltaic panels, and what would happen to the installation cost, the initial cost. The initial cost tends to kind of drop rapidly. It kind of follows the experience curve. And for most technologies, it's covered learning by doing and learning by doing effect and economies of scale. So we have that declining cost. But on the other hand, we have so much uncertainty about actual performance of these emerging technologies. In this case, the solar and PV panels. And by the way, they degrade over time. So their efficiency decreases over time. And we have some uncertainty in that regard as well. On the other hand, the utility market is volatile. It's kind of very volatile, because of the energy market in general. Like if you look at the price of oil, the price of other sectors of energy, you see that volatility somehow translate into the electricity market that we all use at homes and businesses. So that volatility is part of the investment. If we are talking about very high level of utility rate, regimes like in California, in some out west or northeast, then you will see the investors going over there. It's not because the Californians are different from people in the south, but because economically it makes sense. It makes sense because they were talking about very high level of electricity price versus a few cents that we pay for kilowatt hour down here in the south. So if we have that volatility removed from the decision making, you would see adoption of a lot of these technologies would be around the country. Kind of you would see a common sort of trend across the country. And what we need to do kind of trade-off analysis between this adoption cost, installation cost versus the benefits we would expect. So the trade-off would get us that optimal point, and then investors' risk profile can be created. So that's an overview. The building energy simulation field, some people here might be from the building technology program. I borrowed this slide from Professor Augenborough. Basically, we have a good methods now, good models that can help us quantify uncertainty about energy savings. We can run uncertainty quantification on building energy simulation. So that's good. So we have some ideas about how the energy saving look like over the life cycle of a building. And that's very important because that helps us to say, okay, if I adopt it today, how much I'm getting in terms of energy saving and how my energy saving profile changes over time. So this is something we can benefit of that. In our framework, we use that as one component. In other hands, we need some sort of a stochastic model, some sort of uncertainty quantification over time to capture the monetary value of that energy saving. What utility companies would pay you, or you have to pay them to get that amount of energy. So combination of the two give me the energy saving benefits of any technology, in this case, renewable energy. On the other hand, we use the data from 76 to 2006, 2007 on the kind of, the price of these PV panels. You see these are the real data. This is the cost. And as you see, as the volume of the production increase over time, economy of the scales kicks in, so you see dramatic drop in the price. So the point is, maybe here it was kind of experiments in the market, but now it's kind of getting mature and probably flat out. So now the investors are secure about, okay, how much they cost. But there is still uncertainty about how much they actually perform in actual settings in different climates. So that should be in consideration. And with the building energy simulation domain, we can capture that as well. Then we run that trade-off analysis. While you are waiting to adopt technology, you're losing money. That's the opportunity cost right there. So the trade-off is accumulated energy saving that you are not getting by adopting early versus installation cost that drops over time. So at some point, these two cross out, and that would give you immediate, kind of a decision rule for investment. And it might be today, for many technologies, the things are mature, there's less uncertainty about their performance, so you have to adopt it today. Otherwise, the opportunity cost is high. You're losing money by delaying your investment in energy efficiency. For some other technologies, you would still not like to see and observe the market, not just the PV market, just the energy market and regulatory changes that impact the energy price. So you will still like to observe what happened in the market, delay your investment, but you're equipped to have that. Like for instance, for the solar ready, as you do your stuff on the, you have your structural system supported for the, and you have additional support for the putting PV off in the roof. You also have wiring in your, if it's your home, in your attic, you can have your wiring done. So because these are going to be huge costs. If you on average, if you want to turn your home, which is not solar ready, probably why not solar ready, that costs you around 15 to 20,000. But with some consideration in early design, early construction, it might cost you maybe less than 1,000 to do extra wiring, extra pipe in the attic, and put some sort of structural support for PV. So that give you a lot of saving and a lot of incentives to adopt these emerging technologies in the future. So it might be down the road 10, 15 years. So what I would like to say, we need to have some of these flexible design strategies as part of the building design kind of mentality. It's not for today, it's for the use for the life cycle of that building, that home. And that consideration, I have one example. I welcome some other opportunities, some other technologies that you think would have benefit and is still emerging, but in future we can adopt that and how we can incorporate it into flexible design strategy. And then we're gonna compare these two, basically compare what is the fix, going today versus delaying that and optimal timing and favorable timing. And you see kind of a difference between the investor's risk profile. In other words, you would see it minimize exposure to negative outcomes because you delay investment. If the situation becomes unfavorable, you don't have to invest. Versus the case that is fixed that you have to go in today. We had an example. It was a solar-ready house, and we compared it with the actual solar house. It's kind of a California example. These are the overview of that case. And we built that electricity profile model. We built that energy saving kind of calculation in terms of some sort of uncertainty about the actual performance of these PV panels over time. So we get to kind of a threshold, optimal threshold for investment. In this case, we consider one variable. If you look at the electricity price and over a period of 20 years, you see this is a threshold for investment. That means the investors wouldn't, this area weighting is more favorable. Why? Because it's early, the things are emerging, and there's a value for waiting. The opportunity cost is not huge, so you wait. But at some point, it kind of flat out means this is the time. And also it considered not losing money as kind of that energy saving benefits that you would get if you implement that correctly in an appropriate time. So as you can see, most of the cases, if you look at across the nation, the electricity utility rate, from the retailer of utilities across the nation, most of them are here. They're still waiting to see what would happen. And if you look at the places already adopted, they are talking about this kind of utility rates. And out west, if you check the utility rates in California and compare it to Georgia, you would see why it's not making sense here, making economic sense. So I'm just kind of explaining, the motivation when I started that, why certain technology adopted faster in the Europe, in California, out west, northeast compared to the south or Texas or other areas. Yeah, owners push it, but there's somehow, investors have to be behind that. So if not making economic sense, if we are talking about few cents per kilowatt hour, so we're just not getting there. That's the bottom line from the economic standpoint of the whole picture of sustainability. We can find out the profile of adoption when it becomes optimal, as well as the risk profile of that. This is basically the probability of getting financial value. And you can see in this particular case, by delaying it a little bit, you get some flexibility. You would have a better risk profile in terms of financial value for that investment. So want to kind of summarize that. Basically, it should not be about just fix a strategy for design, particularly when it comes to some kind of emerging things like sustainability, energy efficiency. So I would like to talk to you. Please come to me, and if you have some ideas, it could be applied at the level of city and regional planning, kind of flexibility for sustainable neighborhood, or it could be at the level of a building or a home. And by that, thank you so much.
Hi, good morning, everyone. I'm Javier Irizarry, assistant professor in the School of Building Construction, and the work that we've been working on that was funded partly by the GTF grant that we received is looking at the situation awareness approach to the architecture, engineering, and construction and facility management decision support system design. So this is what I would like to tell you about the project that we've been working on, why we chose the facility management area as a testbed for this project. I'll explain the concept of situation awareness and then some of the areas that this concept has been applied. And then I'll tell you a little bit about applying the concept of situation awareness to the area of facility management. I'll tell you what methodology we use, the goal-directed task analysis, and what that entails, And then what we did to apply that method to the area of facility management in our study. I'll briefly go over some of the results, some conclusions of this part of the study, and what are the next steps and what we're working on next. So why we chose facility management as a test bed, we realized that facility managers work in a very complex and dynamic environment. Buildings are like living creatures that have to be taken care of from their conception through their decommissioning. So it's a very dynamic environment with a lot of problems. The facility manager, as we see the profession, should be capable of having an accurate mental picture of the environment that they have and all the challenges that they have to face. They need to be able to understand all the goals that entail their job in order to come up with the most acceptable decisions to maintaining the facility. We also believe that situation awareness can help these professionals to understand what their specific information needs are and how to better address the decisions using the required information. The outcome of the process of applying situation awareness to this profession is a hierarchical situation awareness graphic that will give the developers of future systems an idea about how to better provide information to the people that need to make decisions in this field. So, with that, I'll briefly introduce the concept of situation awareness. This is something that comes from the human factors domain and has to do with how people cognitively process information and basically make decisions. So think of it as an engine that drives the decision-making performance of the user of that information in very complex and dynamic environments. So there's three hierarchical phases to this process. The first one is where the person or the user has to perceive the information or the elements of the situation around them. Then they have to comprehend, basically make sense of that information, process it in their minds, and then they have to project what the outcomes or the results of their decisions will be into the future. So it's a cognitive process that goes through those three steps. So where has this been applied before, and why we became interested in this method to apply it to AEC plus FM, and we started with facility management? This is a concept that has been applied in the military. So, think about military operations where you have different war fighters, if you will, and they receive a lot of different information that they have to process in order to make decisions on where to take supplies, where to take strike forces, etc. So that's one of those areas. The second one is aviation, where the main goal of the pilot in that case is to basically take off and land safely. So they receive all this information from traffic control, their navigation charts, and they have to process all that information in order to navigate from point A to B and do that in a safe manner. And in healthcare, it has been also used to make sure that, for example, nurses and doctors communicate the right information at the right time to avoid costly mistakes by, for example, giving someone the drug that they were not supposed to get. So that is the motivation to use this. It's mainly from the military application. We think that the AEC-FM field is kind of like a war. It's a war against cost, against time, against failure rates of equipment in buildings. So we have to basically manage all the resources that we can to accomplish the goals of the mission, which are to construct facilities on time, on budget, and maintain them at the lowest cost possible and providing the best environment for users. So in facility management, how we thought about addressing those challenges, recognizing that it's a very complex environment that has a lot of information that the facility manager has to process to make decisions on equipment replacement, equipment purchases, and other things, and then reach the optimal decisions that will achieve their goals of their mission. But we don't clearly understand what are all the pieces of information that they'll have to process, and also what types of decisions they have to make. So for that, we are applying this method in order to provide facility managers with a filter that would give them the right information at the right time, taking advantage of technology in order to make appropriate decisions. So this is the method that we use is called the cognitive directed task, or the goal directed cognitive task analysis, developed by Ainsley. And it has these 4 steps, in which the first one is the user has to identify, or we have to identify the key decision makers in the facility management environment. Well, is the facility manager. Then we have to identify the major goals and associated sub-goals for that person. Then identification of the primary decisions that are needed to accomplish each of those sub-goals that will contribute to the main goal. And then identify the situational awareness information requirements that the user will need to be able to make those decisions. So what we did is we did a structured interview. There were one-on-one interviews with 6 facility managers in the Atlanta metropolitan area. Those are considered subject matter experts because of their experience and level of knowledge in the area. They were about an hour long conversations, and the result of those conversations are called the hierarchy charts. And the hierarchy charts are basically flow charts that describe what the main goal of the position, or in this case the facility manager role is, and then all the sub-goals that would help them to accomplish the mission of the main goal, and then all the pieces of information that contribute to those sub-goals. So talking a little bit about the results, we found that the main goal for the facility manager, in this case summarized here, is to manage the facility with safety and productivity in mind. Safety for the users and productivity for the users, but also productivity of the resources that are employed. And then there's all these other sub-goals, like monitoring activities within the facility, determining the facility needs, managing facility resources, and below that, then we would find all the pieces of information that would contribute to them being able to make those decisions. And for example, a little more broken down, the goal of sub-goal of monitoring activities within the facility are described here. We take, for example, the information or the situation awareness requirements. They have to ask themselves a question: do facility managers understand the contracts to get the best value services which they are contracting for? So they have to get all these pieces of information, including the previous contracts, determine the total scope of the contracts, clarify price ranges, and take all that information and process it in order to answer this question and accomplish that sub-goal. So this is the process. So, in conclusion of this stage of the research, we find that situation awareness and its application to the facility management field has the potential to enhance the ambient awareness, or being aware of the critical pieces of information that they'll need to get a hold of to be able to make the appropriate decisions. If they know what the key goals of their position are and apply those situation awareness concepts, then they'll be able to make those decisions efficiently. And the last one is that this methodology is appropriate to develop human-computer interfaces that will allow facility managers to access the information that they need to make those important decisions. So what are the next steps? Currently, we're working on a project called InfoSpot. And what we're doing is we're looking at the application of augmented reality for assessing building information that would help enhance the situation awareness of facility managers. It's a low-cost, complete augmented reality solution, self-contained in a mobile device, and we brought an example of the prototype that we're working on. It's a mobile application that will track the user's position, and the user will be able to, through augmented reality, look at information in their environment about the different objects that are included. And we're doing it at this point with survey observation points, or SOPs, where the user would have to stand in order to geolocate themselves in reference to everything else in the space. So this is what one version of it looks like, and what this is this virtual reality model version, which the facility manager can use from any room in the facility, and basically panning around, he will look at all the information or all the objects that are included in that space, and by touching one of those objects, then the information about the object will come up. So the information that is provided to the facility manager through this interface comes from the results of applying the goal-directed task analysis and the situation awareness approach to develop this interface and the information that is provided by the application. And with that, I thank you very much for your attention.
As Leslie mentioned, my research is in digital design and fabrication, especially in the area of parametric surfaces and digital places. And these two research agendas are synthesized in architectural projects. And that's what architecture is always trying to synthesize. And as an architect, of course, I'm interested in projects as well. Parametric, within the research agendas of parametric surfaces, I mean, you can see a series of research projects, and Lichtraum, that specific research project, is part of that agenda. And digital places, there's a series of projects, two which are usually manifested in gallery installations or exhibitions. And these research areas are then synthesized in projects, which are in most cases competitions. So you see a series of competitions over the last years, and these projects then inform sometimes publications, which you can see with the little blue dots. And sometimes also some of these competitions are winning entries, and also build entries. The project inform publications in not just conference proceedings and journals, but also a lot of architecture magazines, newspapers, and a lot of architectural blogs, and they influence other schools. For example, you can see on the very top left, this is from the webpage of the Hong Kong University, which are using my image to advertise for a workshop in parametric design. There's an endless amount of different web pages. And of course, they also lead to invitations to teach abroad and teach at other schools, and also workshops which are related to software. The main interest in the research of parametric surfaces, there are four kind of main themes that are always carrying through in parametric surfaces. The first is there's an interest in modular systems, and what you can see here, this is a partition. It's one of my first projects 15 years ago, made out of hair rollers. It's for a hairdresser, and so it's the hair rollers, and it's stapled together. It's my idea of sustainability, which is that you can actually feed every material into endless industrial circles. That's very unusual, in architecture, if you just think about it. And the second is an idea of variation. And what we saw in the last years is that we moved from, this is an image I created from a square, and then the square is animated. So this animation, the variation comes like through animation. But in recent years, like we use scripting and coding, and that's a pattern generated in Grasshopper. This is a title of a book, title page of a book called Designing for a Digital World by Neil Leach. And what's interesting is it's a book from, it's published 2000, and I was just graduating from Columbia. I was still in school, and I did this competition, and I experimented with scripting like fairly early. There was no Grasshopper at the time, and there was no Rhino at the time, so these tools didn't exist. The script that I used for that image was it's a primitive object, a cube, and then it's a very primitive script. It's just basically stretching, scaling, and rotating the cube. And what's interesting is if you kind of consistently apply like rules in different ways, you can actually generate form. And so it's like this kind of like wave structures, not just an overall form which is then populated, but it's actually a form that emerges from like a consistent application of a set of rules. I didn't write like any paper at that time, like I was just graduating from school, but I really like experimenting with scripting. The third interest is in the material of plastics, and I think plastics is a material of the future. There is in what you can see at the moment is that the chemical industry is changing from fuel-based plastics, and that's why we didn't like plastics in the last years, because it's not environmentally friendly. But the chemical industry is changing from fuel-based plastics to bioplastics, and there's a whole new palette of materials available which the industry doesn't really know what to do with, which come from recycled materials and which also come like from biologically fabricated materials. And it's also an aesthetic, it's also an, what is also a responsibility for like an architect is not just to figure out like new ways of introducing that material to architecture as a building material, how to connect this material, how to build with it, how to use like it structurally and as an envelope, for example. But it's also how to provide like a new aesthetic, which goes like along like with if you want to give like plastic a material which has a sort of bad image environmentally, but to give the material a new image, it's an aesthetic problem, which is also an architectural responsibility. And if you look at the properties of like different plastics and you compare it with existing building materials such as glass, I mean, it becomes obvious that it's definitely an alternative and an interesting material to look at. And the fourth interest is the hybridization of building systems. What you can see is a modular-based system, and they used to create an envelope for a cover for a park, basically. Or in like more relation like to that specific project Lichtraum, it could be also used to create surfaces, for example, that are sometimes more open and sometimes more closed. Lichtraum is a project that is a self-supporting solar screen that is designed to maximize visual comfort. So there's two big challenges. I mean, one is like to build a self-supporting structure, a self-supporting screen, and then the second one is of like how do you maximize, I mean, how do you reinvent a daylighting system? If you want to invent a daylighting system, the first thing I did is I looked at every kind of possible daylighting system that is out there. For example, prismatic divisions, optical divisions, overhangs, light shelves, fins, buffers, Venetian blinds, you would say, louvers, brise-soleils, shutters, and so on. And there's a whole existing daylighting systems. And then it is important to figure out, to understand the behavior of like these different systems. So for example, if you look at the lighting shelf, you can optimize these systems based on a specific location. So that's what you can see here, what I'm doing with a lighting shelf for a specific location. You can then also think, if you know the behavior of the system, and you see like on the right the graph, and the way the graph works is on the horizontal, there's basically where the window is, and then it's further away from the window if you go to horizontal. And in the top you see the illuminance in lux, and the comfort zone would be like right in the middle zone. So you want to be like right in the middle zone. So what you can see, like at the light shelf, for example, you have like a horrible condition, like if you sit very next to the window because you have glare, so it's like it's above the comfort zone. But if you have a very good performance, if you want to project like light very deep into the space, versus a louver system, for example, you have a very good comfort, like a very good performance close to the window. But it becomes horrible if you go like deep into the space and then you lose like the light necessary. What you can think, if you know the behavior of different systems, you can then start thinking of connecting and combining them and creating like hybrid systems. So that's what I was speculating with a model that I had earlier. And I can keep this around. Which is basically a system that is built from cones, and the hypothesis is that if I can fold like a cone in different ways, I can actually use it to reflect like light into a space. What we did here, and this is also with the help of our PhD students, of course, is to simulate that system, to model it, of course, like in the computer, and then to simulate it in Ecotect and in radiance. And this blue area that you see here is basically an area that is generated from like 100 different variations of like these lighting cones. So you can see the variation is sometimes it's compressing the screen, tilting it, or scaling it differently. If you then think about like the advantages and disadvantages of the different variation, you can think about combining them into a single system, creating a screen that actually performs like similar to a lighting shelf on the top and similar to a louver system on the bottom. So it's kind of creating there's an architectural interest behind this project, which is to like not having separate system, but to combine like system into like a continuous surface. So there's an idea of a conceptual idea of continuity, which I'm interested in as an architect. So the goal is, in a way, to look at the advantages of like the different systems and to try to flatten like this curve to get a good performance close to the window and deep into space. If you have like a screen which is a variation, the question is how do you generate the variation? And there is three variables like within the system. One is, and this is a section like through this cone. One is to fold the system. The second one is like to tilt the system. And the third one is to scale it. The next challenge is then, and that becomes really the architectural challenge, is of like how do you construct it, how do you build it, and how do you detail such a system in that small model, which is very small. It is very easy to connect. I mean, it's still a clever detail because it doesn't use like any other kind of material to connect. So it's just has these flanges which kind of fold into each other. But it would not work, of course, like in a larger scale. To just look at it in a much larger scale, we use like different techniques to build it rather than folding it. We use a combination of like vacuum forming and drape forming plastic. So you can heat the plastic and you can put the plastic in like a final shape. And the way it is connected, it just sits on like top of each other, which is then has bolt connections, which creates a problem because it creates hinges basically. So you have like a kind of a flexible system, which is not really entirely stable. What is interesting is if you add form and if you change like the complexity of form and if you add curvature to it, then you create a tension within these connection points, and you can actually build extremely lightweight structures. And that's an image I took from the AIA Pavilion in New Orleans. Another technique is that you build it in a very similar way than actually the small model. And rather than having like these tabs, you would just create like bolt connections, but connections in the other way. This is actually very interesting structurally, because if you use a material and that has a memory built into it, like specific high density polymers, you can fold that material, you can soft fold it. So that means if you cold bend the material, then you would kind of destroy like the internal quality, the internal structure of the material. But if you don't destroy the internal structure of the material and just bend it, the material would keep the memory and would try to kind of fold back. So if you create this in a sequence, you build a tension into the surface, which is interesting structurally, of course. You can do this in one direction, but you can also do this in two directions to create like different depths. And you can, of course, then fold this like in different way, completely compress it, for example, which we did like for a pavilion which was finished in October in Paris for the New Blanche Art Festival. And I just got a letter from the Cultural Ministry in Paris saying thank you for like a great project, which is very nice. Of course, like behind this, and this is kind of nice diagrams to communicate the project, but behind this there's of course like a whole kind of a lot of work that I did together like with Yumin Su, which is a PhD student with Fried Orenbrook, and GTA students like for that helped me to create like a lot of different simulations. And what you can see on the left top is we have like the cone with like the different measurements. And on the right you can see like a list of all kind of possible dimensions, running like every kind of possible scenario and variation, and seeing like how this would perform. So you can see like an image like radiance. You create like tons of these diagrams, different study models, different models. You need to kind of rebuild these models in Ecotech in order to build like the simulation, which is like very kind of time consuming. Creating these curves, but you also in radiance you create like you can render an outcome that gives you like a very good idea of like how the lighting quality within this space would really be in reality. And of course there are still issues, like there's in the middle you can see here the material is like the material finish. We are still in the process of like running different simulation of looking at different finishes of a material. The project has been, a larger aggregate has been built in two galleries now, like one in Berlin and one in an architectural gallery, Comessé, in Rome. And this is how I traveled with like a small model. There was a small model, is a smaller aggregate in Berlin. It's my famous suitcase with a lot of like hundreds of like modules and spread out like on the floor, and then connecting like all of these different modules into like it was a small aggregate in Berlin, exhibited in Berlin. And then I changed the size of the module, much larger, and used the same detailing, and introduced like all possible variations. So it's the size, the orientation, and like a scale. Here you can see like me connecting it. It took me like a week to connect 2,000 pieces. And you see from the bottom and from the top, and it's the entire exhibition with the large piece and like smaller study models, and all 11 possible ways of like folding the module. What's interesting is if you fold it, it also informs like curvature based on the folding technique, the different orientation and the effects it would generate, the sizes. So it's like all different pieces that all had to be like numbered and logistically organized in order to assemble it. And the script, which basically combines all of these three different parameters in one system. And if you run the script, you get something like that, and it constructed looks like that. And here you can see like detail shots where you can see the different sizes and proportions of these modules. So they're really all different. It's not just a perspective effect. And so if you look really close, I mean, you can see like some are more stretched, some are more smaller, some are larger. And the next step is, I mean, to increase like the size of this. So what you can see like on the right, and this is this is CNC templates. It was like with 60 large sheets that were like CNC'd in the AW in our digital fabrication lab. And this is assembly process and building like a larger pavilion. That was the same pavilion that I showed previous, like in Paris. What you can see on the right is Sabri Gockman, who is like a PhD student with Lars Spybrook, who flew into Paris and to help me with the project. It would be impossible to do that all completely alone. This is a projection you can barely see from like the artist Damien Valero, like in that pavilion in Paris a couple of weeks ago. And a piece of the pavilion was also exhibited in September in the Paris Fashion Week. And so there's also an interesting dialogue, like not just architecture, but there's also a relationship like to a fashion which is totally coincidence. Thank you.
Thank you. And we'll now entertain some questions. Professor Easton.
I want to ask Professor Shree, in college we learn economics, of course, there's some notions of natural supply and demand. But in fact, the government, with regard to subsidies, there is no natural market. So how do you deal with the questions of subsidies, variations in subsidies on energy prices, energy distribution, the large power transmission lines that are required, and down at the residential level, these things are all impacting also. You have a way of dealing with the externalities?
Yeah, I mean, the way I captured that is there is a model for price, energy price, retail price of electricity in this case. And as you mentioned, it's really a function of, that's by itself is a field in economics. People are studying that supply and demand. Actually, the utility providers do that very well, with kind of, contracts they have and the subsidy. If things change, then, I can have different scenarios analysis by that, and analyzed by the model. Like you propose a regulatory regime that impact prices, on average expectation goes higher. So I can apply a higher value for that expected value. And yeah, that's exactly could be done, could be captured. But I'm just looking at the high level. I'm not looking from the dynamics inside, but the dynamics inside I can capture it in terms of different scenarios for the person.
I have another question. So some of the work that Professor Reether's doing deals with light usage and energy usage in some ways. It would be very interesting to see what the cost linkage is between the two efforts. Very analytical versus much more geometric and composition.
You should talk.
I'm going to add something lastly. I don't know if Journal has seen the NSF call for origami applications.
Absolutely, and I put in this.
Okay, because I think this one fits.
It's made for me.
They're waiting for you,
Questions? Yes.
Yeah, Dr. Irizarry, the data that you captured in the situational analysis for your model that you demonstrated, is that interoperable so that it either can be or maybe it already is incorporated into a BIM model? So that you've got one resource?
Actually, it came from a BIM model, but the BIM model doesn't have information about the objects within the space. So that's the information that we get from those interviews is what information about the objects a facility manager would need to perform their tasks. So that's the information that we added to that model.
Other questions, comments? No? Any more? Well, let's thank our speakers again.